What comes to mind when you think of the word asteroids? Well, you probably imagine gigantic astral bodies capable of eradicating entire biospheres. I mean, they did the same thing to the dinosaurs by causing a mass extinction 65 million years ago. So why can't they do the same thing to us, you might ask? Well, if you're thinking about asteroids like that, then you're just being paranoid. The way I see asteroids is that asteroids can be the key to a future of rapid technological and economic growth in a way and on a scale never seen before in human history. And with the development of entire asteroid mining industries, we can expect other industries to pop up, such as space tourism, for example. And in that future, despite all these advancements, there's going to be a major problem that we're going to face. And that problem is about our fuel. Now, if we're going to understand this future problem, there's going to be three things that we need to look at. The first is that the number of rocket launches is increasing exponentially. For example, according to the US ITC, or the US International Trade Commission, between the years 2018 to 2022, the number of rocket launches in the US alone grew by 152%. Now, this is just in the US alone. Don't get me started on the global launches. The global launches in the same period have shown a growth rate around 14.6%, with a record-breaking 186 launches in 2022. 2023 broke that record with 223 launches. Based on these trends and current developments, such as the development of a space tourism industry, we can expect there to be a massive demand for rocket fuel in the future. What we need to look at is that the fuel is changing. Hydrogen, which is the mainstream fuel source, is being replaced by methane. And you can see this development occurring in several companies such as SpaceX, Blue Origin, and Rocket Lab. Now, the reason why, you may ask, is because hydrogen is pretty problematic to deal with. One of the things that hydrogen does is that it can cause the materials around it to become brittle and lose their mechanical properties in a process known as hydrogen embrittlement. And this is especially the case when you're dealing with liquid hydrogen, which is insanely cold. To make matters worse, the boiling point of hydrogen sits at around negative 252.9 degrees Celsius. This is lower than the oxidizer, which is oxygen, which sits at around negative 183 degrees Celsius, approximately. This doesn't seem so problematic at first. However, when you think about it for a little bit more, you can start to see why. When you're trying to keep something cold right next to another material which is around 60 degrees warmer than it, that's going to be quite a difficult task to do. However, methane, which is the better alternative, can sit at temperatures at around negative 161 degrees Celsius, and this is much more closer to the oxidizer, which makes it easier to insulate. Also, methane doesn't cause embrittlement, and this is one of the several reasons why companies are making the switch to methane. Now, this all leads us to our third point. Because methane is quickly replacing hydrogen as the next mainstream fuel source and the number of rocket launches is increasing, there's going to be a massive demand for the amount of available methane for rocket fuel purposes. And the thing is, current methods of production on methane on Earth is incredibly disastrous for the environment. I'll just quickly quote from the US Energy Information Administration. Drilling a natural gas well on land may require clearing and leveling an area around the well site, Well drilling activities produce air pollution and may disturb people, wildlife, and water resources. Laying pipelines that transport natural gas from wells usually requires cleaning land to bury the pipes. Natural gas production can also produce large volumes of contaminated water. Now, this all goes to show how disastrous methane production is for the environment here on Earth. Even if we ignore the glaring environmental issues right here, there's going to be a problem that we're going to encounter. And that problem is of transportation. For example, if we're trying to transport methane fuel from Earth to Mars or from Earth to the Moon, it's going to be pointless because we're just burning fuel to transport fuel. Like, that makes no sense. So what do we do? How do we get around this? Well, that's actually why I'm talking to you right now. I'm here to propose a new, eco-friendly, and revolutionary way to produce methane in space to ensure that we don't run into this future. Now, my proposed idea is to use methanogens to biomine methane from volatile-rich carbonaceous chondrites found on near-Earth asteroids, which are asteroids that have an orbit similar to that of Earth. So, I suppose I should be telling you about our methanogen, but before I begin, I'll give you a little bit of a rundown on what methanogens are. So methanogens are a type of anaerobic bacteria which are unique for its metabolic process. In fact, what it does is that it metabolizes a carbon source and a hydrogen source to produce methane as its output. Now, these types of bacteria are found commonly in wetlands and in the guts of animals, such as ruminants. And the interesting thing about our bacteria is that it doesn't yet exist. In fact, it's going to be a chimera of two different bacteria. What are the two bacteria that it shows, you may ask? Well, the first one is going to be a methanogen, and it's going to serve as the base genome for our bacteria. And this bacteria is known as Methanothermobacter thermautotrophicus. And the reason why I chose this bacteria is, well, based on my calculations with other bacteria and this bacteria, I found that this bacteria had the quickest time to produce 1 ton of methane from 37.5 tons of volatile-rich carbonaceous chondrites with 5 kilograms of the bacteria itself. If you want more details of the calculations, I linked the original article to this idea down in the description. So, in order to choose our second bacteria, we need to identify what's going to be on the environments of an asteroid. So there's going to be a pretty powerful vacuum because of the vacuum of space. And there's also going to be a lot of radiation, like gamma and ultraviolet radiation on the surface of the asteroid because of space, and there's no atmosphere to protect the bacteria. The other thing is that it's going to have to worry about dryness and temperature fluctuations. And it seems pretty big ask for any organism. However, there's one bacteria that can survive all of this, and it's named Deinococcus radiodurans, also nicknamed Conan the bacteria for how hardy it is. For example, there's a study conducted on this bacteria, and it was able to survive, get this, 10,000 grays of gamma radiation, and 1 gray of gamma radiation is already a pretty big ask on the human body. Now, even if we successfully splice the 2 genomes of the bacteria, there's still going to be a massive hurdle that we need to overcome. And this is the part about 1, controlling the asteroid so it doesn't continue to spin around, also known as tumbling. The second part is containing the methane so it doesn't leak out into space. Third part is stopping debris from impacting the mining field. Now, this will all be solved with our mining vehicle. In terms of how the mining vehicle would work, first it would go up to the asteroid, and then it would launch a net. And then the net would fasten around the asteroid, gripping around. And this net would be made out of a Kevlar Vectran composite to make it strong yet flexible. And the interior layer could be made out of Xylon to reinforce it a little bit more to stop the abrasion from the asteroid's rough edges. Then there would be a secondary net which would be made of a laminate of Mylar and EVOH. So this would be a thermal insulation layer. And the outermost layer would deploy and wrap around all of them, and this would be made out of Kevlar and Vectran, so that it would stop the debris from impacting it too. While all these nets are deployed, the RCS thrusters, or the reaction control system thrusters, would then begin to control and stabilize the asteroid to stop it from tumbling or from spinning around in random directions. Now, once the stabilization has been completed, from the main hull will come out a proboscis. At the tip of the proboscis will have 5 kilograms of the bacteria. Now, all of these bacteria are dormant because one of their major genome donors, which is Deinococcus radiodurans, can be put into dormancy. So we'll put all these bacteria into dormancy by dehydrating them. And when it reaches the asteroid and when it touches the asteroid, then a 1 kilogram of feedstock will be dispensed, and then that will jumpstart the process of methanogenesis and wake them up. And then while on the asteroid, it will take a few months, and then over time they will continue to produce more and more methane. And while this is happening, transport vehicles such as rockets or some other type of vehicle could come along and dock with the outlet valve. Now, to be honest, this was a very oversimplified version of how the mining vehicle would actually work. If you want to know more about how it works in depth, I'll link the same article as I mentioned earlier down in the description so that you could check it out. Even with all of these mining methods, even if we had the mining vehicle, even if we had the bacteria, even if all of these things worked out, it wouldn't matter if we couldn't find a way to identify the asteroid that we're going to mine. So in this next segment, we'll be talking about prospecting processes that we can do to identify the suitable asteroid for this type of mission. Now, when it comes to asteroid prospecting, it's all in all pretty expensive. In order to reduce the cost, we could send a special type of satellite known as CubeSats, which are incredibly small satellites, which also makes them incredibly cheap to produce and also to launch. When it comes to the telescopic bits of prospecting, we can expect within the next few decades that telescopic technology will increase by great strides. When it comes to identifying the ideal asteroid, there's one bit that I left out, and this is the bits about the metrics of diameter, spin state, shape, mass, density, and also the delta V, which I've all covered in the article that I made about this idea, which I linked in the description, so feel free to check it out. But again, I must warn you, it's a bit of a long read. Even highlighted a couple of technologies that we could apply to this mission if they are developed correctly to increase efficiency, lower cost, and make the mission much more easier. One of them is fusion technology, because fusion technology, it's green, it's also abundant, because one of the main fuel sources for the fusion reaction is deuterium, which is widely available in seawater. And also it can provide a significant amount of energy compared to nuclear reactors or even solar panels for that matter. Because right now what we have are solar panels and nuclear reactors. Solar panels, well, we can't ensure that there's going to be direct sunlight to power the systems all the time. And adding a nuclear reactor is going to be a bit challenging because we need to ensure that the bacteria survives in order for this whole mission to happen. Even though I mentioned that one of the gene donors for this bacteria, Deinococcus radiodurans, is insanely radio tolerant, it's just going to hurt the mission if we add more radiation. Another thing is we can improve is the improved telescopic and prospecting technologies, as I had highlighted earlier, because there's going to be a lot of time for that technology to improve, which is the next 10 to 30 years. And then gene editing technologies can improve significantly. As I mentioned earlier, the time frame is going to be pretty long to improve. And with improved gene editing technologies, we can expect the cost to develop this new genetically modified bacteria to go way down, and also the speed of the genetic modifications to improve significantly, also while reducing the risk of something going wrong. And then lastly, AI and artificial neural networks. This could help a lot. For example, when the mining vehicle has captured the asteroid, we could use AI to potentially determine how the RCS thrusters would move so it can stop the asteroid from tumbling. And also we could use AI to potentially improve telescopic technologies to make detection of asteroids faster. Just to reiterate how much demand there could be within the next few decades, SpaceX has mentioned that its Starship could fly international flights, and as you can imagine, that's going to be a lot of rocket launches. And also considering the fact that Starship can hold up to 1,200 tons of liquid methane as fuel. And another thing that I should mention is that this wouldn't just be a standalone market, because we have a lot more fuel. Assuming that this technology that I had mentioned gets developed properly, we could expect there to be, greater advancements in the space tourism industry or in other related space industries. Conclusion, this method could be the way we source methane for rocketry purposes. And with developments in AI, in fusion, and in biotechnology, and in asteroid prospecting, we can expect this method to be a lot cheaper and a lot more efficient. And while this future does seem a bit distant, we should be thinking in the long term, my friend, because if we think in the short term for short-term gains, that will not ensure our long-term success as a civilization. So we should be thinking in the long term if we want to ensure our technological, economic, and social growth. And while asteroid mining and launching the first asteroid mining mission may seem daunting, that should not be stopping us from sending that first one.